Hello everyone and welcome to Atencephalon Lectures. Atencephalon is a research company that employs expertise in neuroscience and computer science with the intent of using a regular computer program to control the brain of a living animal. Atencephalon has developed research in this field, and this series of lectures underscore our belief in this possibility. This is the fifth in our series of lectures. Links to the first 4 lectures are provided in this video. In this 4th lecture, we shall be looking at an ALU circuitry designed with neurons. By ALU, we mean the arithmetic and logic unit circuitry designed with neurons. All right, in our last lecture, the 4th lecture, we were able to take a truth table, a 3-input truth table like you see here, and we're able to design a circuitry using neurons to be able to implement this truth table. Clearly, we talked about excitatory neurons, inhibitory neurons, and how they contribute to this circuitry. Right. So in this one, we're going to be looking first of all at what is processing. What is processing? We all hear that in a computer there is a processor, there is processing that takes place in the computer. The brain also is a processing organ, right? It takes input, it does processing, and it gives out output. So we want to look at processing. So take a computer, for example. Processing in a computer would involve that you have what we call a control unit, like we have at the bottom here shown in blue. Then we have the arithmetic and logic unit, which is what we're going to be talking about today, the ALU, arithmetic and logic unit. And then we have storage. So sometimes you might have a confusion of terminology. So in this video, we just call the arithmetic and logic unit and the control unit together. We call that the processor. In some other literature, you might see that they may call it central processing unit. But just know that central processing unit will involve not just the arithmetic and logic unit with some memory elements, storage elements, RAM, chips, registers, whatever. Once you put memory together with the arithmetic and logic unit and the control unit, then you can call it a central processing unit. So here I have a bigger picture where I've written a central processing unit. We have included storage and then what we call the core processing, right? So this storage could be, in the case of a computer, it could be RAM, it could be ROM, it could be even your flash drive, it could be your hard disk, right? Or nowadays we use SSD, okay? It could be anything where you can store something. It could be a cache memory, it could be registers. So in a typical processor, what you would have is that you have the arithmetic and logic unit, control unit, and some processors that are, and some registers that are packed together with this, and they are called the central processing unit. Now, let us also say that depending on the architecture of a computer, in some processing, there's not just one processor. You can have several processors. So you can have a computer system that has several processors. For example, you can see other smaller processor here, different from this central processor that we have, the main processor, the coordinating processor. So we might want to call this coordinating processor the main processor. Then you have other smaller processor. So in this architecture, we would say it's a multi-processor system. So this is a computer system that has many processors, right? Howbeit, there will be a central or a main processor, right? And then you have other processors. In others, you can even have all the processors of the same ranking, such that programs are just distributed among these processors, all right? But however, in more organized systems, you have a coordinating processor, a central processor, right? Sometimes even this central processor may consist of smaller processor. So this is like a processor in a processor. So you have arithmetic and logic in the control unit. You have like 3 of them inside a package called the processor. So in this way, the terminology we usually use is, we call this a core. So this will be a 3-core system. If it's 2-core, we say dual core. If it's 4-core, we say quad core, and so on. So a core system is one in which you have smaller processing units within the main processor. So in this case, what we see here, we have 3 cores within this central processor. So there are several possible architectures you could have. As technology evolves, people play around with a lot of things and see which one is more effective and which one can be dropped. Sometimes they do something and discover it has a problem, and then they go back to what they were doing before and make some amendments. So, but generally, a processor will have an arithmetic and logic unit, control unit, one or more. And then it might have some storage, and then it might have a central storage and all that. And then there is inputs that are fed into the processors and output. Such inputs in a computer could be a keyboard, a mouse, a joystick, a light pen, a scanner. These are possible inputs you can use with a keyboard. It could be a microphone. Outputs could be maybe a printer, a plotter. It could even just be graphics display, a monitor on the screen. And it could be so anything. Anything that will make the computer to bring out an output is called an output device. All right. So you can even have, like I said, several architecture where you can even have several processing units, and even within the central processor, you can even have cores. Now, usually when you have this architecture, they don't like to call this other smaller processors. They'll just give it give it other names, you understand? But we know that going to the heart of what they do processing. For example, one of them may be a sound blaster card. Just all it does is take data, chunk those data to be able to generate sound. Some will be a video graphics adapter card and network interface card that has maybe processing for networking and all that. So different smaller processing taking place. And then you have the central processor that will have many cores, like we said, and even have some hubs. I know that, for example, Intel back in the days used to have North Bridge and South Bridge, where the North Bridge took on some functions and the South Bridge took on some functions different from even the processor. Along the line, they evolved and changed to a platform control hub. So they had the platform control hub. And later, they also further evolved. And now, what they have is a CPU and the platform control hub put into a package, which should be called. So if you open that package, you are going to find 2 dice. One is the CPU, and then the other is the platform control hub. AMD had its own. They just called it, then it used to be Fusion Control Hub. Later, they changed it to a chipset. So you can have different types of arrangement. Within this processor, what we've called hubs here are just special circuitries that help this processor to achieve its job. In Intel, for example, they call this on-core or system agents. Just call them system agents. Usually, it will be an integration of things that were formerly in the North Bridge and South Bridge, and later migrated to what we call the platform control hub, and several things that will make the processor to be able to talk, to be able to take in input, store it, do some processing, and generate outputs generally. So generally, this is the layout of what processing takes place. And like I said, you can have terminology where they will say this is the central processor, and it will have the control unit and the arithmetic and logic unit. And then once it has some memories, we call it a central processor. Sometimes central processor just means all this ALU, CU, and storage. Right. So if we look at that, we will see that the components of the ALU really, I just took this picture from exploreembodied.com. You can visit their website, exploreembodied.com, and you see other things that have been discussed there. I encourage you to do that. They really have very beautiful videos that you can learn from. All right. So I took this picture from that place, and this is a picture of just a 1-bit ALU. That's an ALU that adds just 1 bit. 1 bit in register A and 1 bit in register B, and you are trying to add them together. So typically in an ALU stands for arithmetic and logic unit. The arithmetic unit is usually done with the full adder, because most of the things we do, whether it's addition, subtraction, division, the full adder is designed to be able to do that thing. So for example, subtraction is just addition with using complementation. That's subtraction. Then multiple subtraction is what we call division. You know, things like that. So the adder can do addition, and from that addition you can do subtraction and division and multiplication and all that. All right. Then we have the logic units. Simple logic like the AND logic. This is an AND logic. This is, for example, a NOR logic. That means an OR gate and then a NOR. This is a NOR logic. And then we have exclusive OR logic. You can have others like that. So you have a logic unit, and then you have the arithmetic unit, which is usually represented with an adder. So what we have in an ALU is that you will send in bits to select. So once you put in your data, the data is AO and BO. That means the first bit of A and the first bit of B. If you send them in, all these operations happen. Then you use a multiplexer to choose which of them you really want the output to come out at FO. So for example, if it was, I just want to do an ANDing of the 2 bits, right? I want to AND the 2 bits, and that's usually for comparison. Maybe I want to see if bit A and bit B, maybe I want to find out if they are the same or if they are different. If I want them to be different, for example, then I would say anytime they are the same, it should be 0. When they are different, it should be 1. So in such a case, you use an exclusive OR gate. So if exclusive OR, remember the logic is only when the 2 bits are different that you are going to have a 1. So if A is 0 and B is 0, the answer is 0. If A is 1 and B is 1, the answer is 0. It's only when A is 0 and B is 1, or B is A is 1 and B is 0 that you have the answer 1. So an exclusive OR logic can, for example, be used to check out if 2 bits are different. So we have different logical operations that we can do using bits, all right? But we've looked at AND logic, how it's been developed, how it's been designed. We've looked at exclusive OR logic in this video, and maybe at a later video we'll just look at how a NOR gate is being designed. But for the purpose of this video, we want to look into a full adder, the circuitry of a full adder. How is it designed using logic gates? And then we'll now look at how we can design this and how it will work using neurons. Okay. So, in a logic gate, this is how you would design a full adder. If you go online, you will find out different websites talk about how this can be designed, where you have to take this truth table and use a Canov map to simplify the circuit, and from there you are able to either using canonical sum of product or canonical product of sum, whichever, and then you are able to come out with this circuit. So this is the circuit of a full adder, where A is the bit, A and B are the bits you want to add. But you know, when you do addition, there is usually a carry in and a carry out. So when you do addition, you get a sum, you get a carry out. The carry out is fed in to the next bit as carry in, and then so this is the circuit that does addition. This is full adder circuit. Enough literature is on this on the internet already. So in a neuron, how would this be done? Remember, we said we have 2 outputs, sum and carry out, which we have shown here, S sum and C carry out. So let's see how the S sum, if you want to get out the S sum, how it looks like. This is how the neuron that will implement this S sum will be laid out. This simplification was done, the truth table was, rather than use a Canov map that we use in a normal using logic gates, in this situation we use the Odunsis method for simplifying this circuit to be able to get out these neurons. So it's the Odunsis method that is used. And like I said, Odunsi is a staff of Atensi Felon. He brought out this proprietary method, and it's been an excellent method working in simplifying many of these circuits that we designed with neurons. Okay, so this is the circuit. This is how the circuit looks like. All right. If you see this arrow, we are saying we are looking at this. We are looking at the sum bit, and we are on column 0. So nothing is happening in this circuit. Right. Let's see how the carry out bit looks like. This is how the carry out bit, this second bit, the carry out bit, the circuitry that we implement, the carry out bit, this is how it looked like. Again, it was simplified using the Odunsis method, and we're able to get out these neurons, this arrangement of neurons. So what we'll try to do is we'll try to fuse the 2 of them together. So we have it concisely inside one bit, and that's what you see I have done here. So this right portion of it is the one that does the computation for the sum bit, and the left portion of it is what we've done that does the computation for the carry out bit. So in the right portion where we do the sum bit, you can see some inhibitory neurons, 3 of them, and 4 excitatory neurons. And in the carry out bit, you can see they are all excitatory neurons. All right. So let's just try and walk through maybe 2 or 3 of these conditions and see how, for example, how is if you have 101 or 011, how, let's walk through it and see how we're able to get out the carry bit and the sum bit. Okay, so we know when it is 0, nothing is happening. I mean, A is not generating any action potential, B is not generating any potential, and the carry in bit is also not generating any action potential. But if we have a situation where we are, let's pick this 4th row where we have A is 0, B is 1, and C is 1. We expect that the sum will be 0 and the carry out will be 1. So let's look at that. So A is 0, B is 1, C is 1. A, no action potential, B, action potential, C, action potential. That is what is represented in column 4. So when those action potentials travel from the axon hillock of B and C carrying, they terminate on these respective neurons. They terminate on these respective neurons. Those 2 neurons sending out action potentials will terminate those action potentials on this respective neuron, releasing neurotransmitters to the synaptic cleft, binding to ligand-gated ion channels that will open up and bring in sodium or calcium, and then the cell will become depolarized. In the case of inhibitory neurons, what they will do is they will hyperpolarize those postsynaptic cells. Anyway, so we land on this. So let's do analysis starting from the right hand side. Look at this buffer. Because it's a buffer, we expect that as the input, as the action potentials get to this postsynaptic neuron, is going to also generate an action potential because it's just a relay. So this buffer will generate an action potential. This second buffer will also generate an action potential. Now let's look at this AND gate. The AND gate is a 3-input AND gate. However, only 2 inputs are being triggered here. Action potentials are arriving at only 2 inputs. So this AND gate will not generate any action potential. Same thing, this AND gate, this first inhibitory AND gate is a 2-input AND gate, but only 1 input is coming in. So this AND gate will not generate an action potential. Same thing will happen in the second inhibitory neuron and the last inhibitory neuron we have here. But the last inhibitory neuron has 2 inputs coming in. So in these 2 inputs coming in, the condition is satisfied. So it will generate action potential. So the last inhibitory neuron will generate action potential, and the first 2 buffers will generate action potential. That is what we'll have in this right-hand side. So let's look at the left-hand side. On the left-hand side, where we want to generate the carry-out bit, the first AND gate here is a 3-input AND gate. Only 2 inputs are bringing in action potentials. So this AND gate will not generate an output because it requires 3 to do that. Going to the second AND gate on the carry-out side, we discover that it's a 2-input out gate. However, only 1 input is bringing in action potential. So this AND gate will not generate an action potential. Let's go to the third one. The third one is the 2-input AND gate. Because it's a 2-input AND gate, the 2 inputs are coming in. This third AND gate, this third AND neuron will generate an action potential. To generate an action potential because the 2 conditions are satisfied. But the last one here is a 2-input AND gate, but it has only 1 input coming in, so it will not generate an action potential. So at the end of this, what we're going to have is that the AND gate generates an action potential, the buffer will generate the 2 buffers will generate an action potential, and the last inhibitory neuron, like we saw here, the last inhibitory neuron here are two inputs. So that last inhibiting neuron will generate an action potential 2. So on the side of the sum, buffer generates, the two buffer generates, and the last inhibiting neuron generates. On the side of the carryout, only the third neuron and expressing neuron will generate action potential. So those action potential will travel and they will go towards the sum in the right hand side and towards the carry out neuron in the left hand side. All right. So when it gets to the carry out neuron in the left hand side, we discover that there are no inhibitory neurons here, and this is an OR logic. Consequently, the carry out bit will generate an action potential, so it will be 1. Let's see what happens in the sum. In the case of the sum, you have one excitatory neuron here telling this neuron to fire an action potential. A second one is also telling this same neuron to fire an action potential, which means 2 neurons are telling it to fire an action potential. However, if you look at the inhibitory neuron, the axon terminal terminates in 2 different areas on the same neuron, the same neuron that is expressing all logic for sum. So 2 are saying do not fire action potential, 2 are saying fire action potential. If you sum this up, this will be 1 plus 1 minus 1 minus 1, and the answer will be 0. Consequently, this neuron expressing sum will not generate an action potential, so it will be 0. Whereas the carry out bit will generate an action potential, which will be 1. And that's what we've seen here. The carry out bit generates an action potential. The sum does not generate any action potential. Right. Okay. If we have all 3 bits, A, B, and carrying, generating action potential. So you have it as 1, 1, 1. So we want to follow this and see if the sum will generate an action potential and the carryout bit will generate an action potential. I encourage you to try others on this. You can take this and on your own walk through it and confirm that this circuit expresses this truth table that we have here. Just walk through it. You can pause this video and walk through it and see if you walk through when it's 001, 011, just check all of them and ensure that this circuit, and maybe leave a comment if you see, if you check it and it's correct, you leave a comment. If you have a problem, if you have any difficulty, you can put it there, and then I can address it at any other later video, or I can contact you personally and clarify your doubts. So let's follow it. All 3 generating action potential. So the action potential travel, and they will hit all the neurons that you have here. They will hit all the neurons that you have here. All the axon terminals will be will release neurotransmitters to the postsynaptic neuron. All of them, since only 3 are connecting to all these 3, so all of them will receive. All right. So if we look at the side of the sum, all the buffer will consequently relay the signals they receive out. So they will generate action potential. All these 3 buffers. The AND gate is a 3-input AND gate, and all the 3 inputs have been activated. So this AND neuron, this first AND neuron here, will also generate action potential. But remember the axon terminal, there are 4 axon terminals that you have here. All this computation we're doing using Odonsis method. So Odonsis method was able to tell us that this neuron will have 4 axon terminals for it to be able to express this logic. All right. So same thing happens in this inhibitory neuron. They will all fire. The AND gate will fire. This other AND gate too will also fire. On the side of the carry out bit, the first AND gate will fire. Why will it fire? Because there are 3 inputs and all the 3 inputs are activated. The second AND neuron too will fire. It consists of 2 inputs and the 2 inputs are activated. The third AND neuron will fire because it has 2 inputs and the 2 inputs are activated. Same thing with the last one. So if we progress this, all of them will fire action potentials towards their respective outputs. So on the side of the sum, we see that all the outputs are fired towards the sum. So let's see. Let's look at the voting. Remember, we are using spatial summation. So let's look at the voting, the summation. So let's see how many excitatory neurons we have here. We have 1, 2, 3, 4, 5, 6, 7. 7 excitatory neurons here. How many inhibitory signals are we receiving? We have 1, 2, 3, 4, 5, 6. 6 inhibitory neurons against 7 excitatory neurons. Consequently, this S neuron, the output of the sum, will fire an action potential because on the net sum of this is 1. So it will fire an action potential. On the side of the carry out bit, they are all excitatory. So no need saying that it is definitely going to fire an action potential. So what you're going to have is the sum will fire an action to potential and the carry out bit will fire an action potential, as we saw in this last column, where sum will fire 1 and carry out bit will fire 1. All right. So the entire of this circuit now can be a nucleus in the brain or in anywhere in the central nervous system where addition is done. This other circuit will be a nucleus or a part of a nucleus somewhere in the brain where computation is done. All right. So if you remember, we also saw that there was a multiplexer. We know how the AND gates and the exclusive OR gates, we've worked with that before in previous videos. Look at a multiplexer. How will we implement a multiplexer in using neurons? Now, typically, the way it is done using logic gates would be to put in logic gates and draw out lines just as we've been doing to show 1, 2, 3. If it's a 2-input logic, then you have 2 raised to the power of 2, which is 4. If it is 3, it's 2 raised to the power of 3, which is 8. If it is 4, it's 2 raised to the power of 4, which is 16. But in the case of neurons, it will not work like that. What we will have is that for you to individually select either 1, 2, 3, 4, 5. Using Odunsi's method, it has been discovered that you would, if it's a 4 input, the maximum you can have is using 2 bits out of the 4 to represent, to identify a neuron. All right, using 2 bits. So you'll find out where I have A, B, C, D. I have to say, like the first one, we have to say C and D, 2 bits, or in the second one, B and D, or in the third one, we have B and C, or we have A and C, or we have A and B. So rather than having 2 raised to the power of 3 or 2 raised to the power of 4 as we have in logic circuits, what we have is a combination. So we would say that if it's a 4 input, using binomial expansion, you would know that the highest you can have will be 4 combination 2. And 4 combination 2, if you do this, that's 4 factorial all over 4 minus 2 factorial, 2 factorial. And what you are going to have is 6. 4 combination 2 will give you 6. So in this, our multiplexer situation, we are going to have 4 inputs, but each of those 4 inputs can only bring in 2 bits per time. Either you're having C and D, B and D, A and D, B and C, and A and C. And those 2 will uniquely select one of this neuron. So when you bring in, say, C and D here, you will find out that the neuron that will be selected, this AND neuron will be selected, and the selector will pick the adder. In this case, we are picking the adder, this adder in this circuit. If you bring in B and D, if what is sent into the multiplexer is B and D, then the second neuron is selected and it will be the AND gate that will be selected, and so on and so forth. So in this case, we only have 4 things to be selected: the adder, the AND gate, the NOR gate, and the exclusive OR gate. You can have several other gates in this logic circuit, in which case we will design an appropriate input for such. So if you have 4, if you are using 4 neurons, if you are using 4 neurons to do this multiplexer, then the maximum you can have is 4 combination 2. If you are using 5 neurons, it will be 5 combination 2 or 5 combination 3. Any of them will give you the same result. If you are using 6 neurons, the maximum you can have is 6 combination 3. You can see that clearly if you use binomial expansion. If it is 10 neurons, that will be 10 combination 5. So really, it is just the number of neurons combination half that number of neurons will give you the maximum you can have in that. So this is how we design multiplexers. Thank you very much, and I'll see you in the next video. Bye.